So today we saw two results about triangles be proven. The first is the Isosceles triangle theorem's converse that says if in a triangle I have two congruent angles, then opposite those two congruent angles must be a pair of congruent sides. In other words, if I have two congruent angles in a triangle, we can guarantee those triangles are isosceles. So what the engine of this proof was again a congruency argument. So in the forward direction of the isosceles triangle theorem that we saw in the last class, it was SAS that we used to get us where we were going, right? And we used SAS last time because the forward direction assumes something about two sides, right? We assumed we have some equal sides, and that let us know something about two sides to use SAS. This time, our assumption is that we have two equal angles, angle B and angle C. And so, given that, it's not perhaps that surprising that the congruence notion that we need is ASA, because we're not able to say anything about sides up front, we're instead able to say some stuff about angles. And so the proof is this really subtle argument that relies on taking the triangle ABC, which is what we want to prove something about, and creating a second copy of it. So the relationship between these two triangles is that we've reflected, essentially. Which is not the kind of argument that we're going to make a lot in the first phase of this course. It is typical of the kinds of arguments that we make in the second half of the course when we start talking about isometries. Remember we talked about what can make two congruent figures different, and one of those things is a reflection. So this is a kind of argument we're going to be accustomed to much later in the course, which is part of what makes this really subtle. But the key to this proof is that because these two angles B and C in our original triangle were assumed to be congruent, when I flip them over, we also get a pair of congruent angles here and here. Right? And the subtlety was that the angles that we labeled C and C prime, so this one and this one, those two are congruent by construction. Because reflection is an isometry, it preserves the congruency of angle C to angle C prime. Same thing with B and B prime. Those are congruent as well, again, by construction. Because that's how we obtained the triangle on the right from the triangle on the left. And so the key link that we need there in the middle is that we assumed that B and C were congruent by assumption. That was part of the hypothesis of the theorem. But then as soon as those are congruent, it gives us congruency of all four of these angles, which is great, because then that allows us to make the ASA argument, because BC and B prime C prime are congruent, again, by construction. They're exactly the same side on these two triangles, which are just reflections of one another. And that allows us to say that the entire triangles are congruent, and then again, we end up making the argument that AB and AB prime are congruent, again, by construction. Ditto with AC and AC prime, congruent by construction. But then, because of the ASA argument, we can also say that AB and AC prime are corresponding sides of congruent triangles, and therefore AB is congruent to AC prime, but AC prime is congruent to AC by construction. And so we get, reading from beginning to end, AB congruent to AC, which is what we were meant to prove. It's a really subtle argument, and it's worth going back over it a few times to make sure that you get all of the different sort of subtle, what do we know by assumption in the problem, and what do we know by how this triangle was constructed? What's congruent to what? And why did we need to show that the entire triangles were congruent in order to conclude that those sides are congruent? So subtle argument, definitely worth rehashing when you get a chance. Our final theorem for today was the angle-side inequality, which tells us in plain language that you will find larger sides in a triangle opposite larger angles. Okay? So larger angles have longer opposite sides. That's the colloquial statement of this. And this, too, was kind of a pretty subtle argument, and it relied on two pieces of information from before. It relied on the Isosceles triangle theorem, which we know is 1.2.6 also, right? We saw that on Friday. And it also relied on the triangle inequality, which is something that we are going to take as an axiom in this course. It was one of the things that our author states at the beginning of chapter 1. We're going to assume that we know this to be true. So that's not a result that we're going to have to prove. In fact, it's not really possible for us to prove with the tools that we have. So we have to take it as an axiom in order to use it here. And we can do that. The authors mentioned it prior. So this proof works using this really, I think, nifty, but again kind of subtle argument about taking a triangle ABC. And because we're allowed to assume that the angle at B is larger than the angle at C, we can construct this magical ray, Bx. So it's a ray originating from the point at B, and it has the property, so we construct this with the property that the angles, that the angle from angle C is duplicated over here by this ray. So these two angles are equal. That's how we construct that ray in the first place. Having now a pair of congruent angles in the triangle BCD, so D is the point at which this ray intersects the third side, which again, unless we know that we have a larger angle at B to work with than we have at C, we don't know that this ray is even going to intersect that third side. So we needed to use that fact in order to even define this point at D. But now, DBC, or BCD, however we want to say it, we can conclude is isosceles. But we can only conclude that because of the equal angles at B and C. CBX and DCB and 1.2.6 are what we needed to make that conclusion. So BCD is an isosceles triangle with CD equals BD. So we have a pair of equal sides here and there. And then because that was an isosceles triangle, we then are able to make this neat triangle inequality argument that says, on the one hand, AC is equal to AD plus DC. By the way, how do we know that that's true? How do we know that the distance from A to C is exactly the same as the distance from A to D and then from D to C added together?
Because it's greater than AB.
Well, no, but that's what we're trying to conclude from here, right? How do we know that those two distances add up to that distance in our figure?
Because the radical B cuts AC in half. So AD is equal to BC. I mean DC.
Well, AD is not, it doesn't cut it in half. It doesn't necessarily cut it in half.
AD and DC are the same length.
I don't think that they necessarily are, actually. No. DB and DC are the same length. But AD and DC are not necessarily the same length. Let me just sort of, let me leave that sense hanging out there, right? But we end up using this along with the triangle inequality because AD is the same thing as, because DC is the same thing as DB, AD plus DB, but by the triangle inequality, that's bigger than AB. Triangle inequality, concluding the proof. But it's worth thinking about, how do we know that those two distances, AD plus DC, add up to AC? Hint, it's in the penumbra of the triangle inequality itself.